Can you tell me if the focus is okay?
That's good.
I'll make it bigger. Is it good? Okay. So welcome to office hours. Good to see you.
Me
Hmm,
too.
Great. So we're looking at special homework number 7. And which problem would you like to look at first?
I actually want to look at the last problem. That
Well,
seems to
that
be the
is
most
problem
complex
4.
one.
Yeah, that is
Yeah.
problem 4. And so problem 4, and I try to work you through it. I try to step you through it. It
Mhm.
says for all A, B, and C in the integers. You read the rest of it to me.
Okay. For all A, B, and C in the integers, if A is not divisible by 2B plus C,
Stop. Let me
then
help you. Let me help you. Hang on. I got to turn on closed captions. Okay, let's try again.
okay.
For all A, B, and C in the integers,
Mhm.
if A does not divide
Oh, it does not divide. Okay. Thank you for
to
that.
B, plus C.
Mhm.
Now, you want to read the rest of it?
Yeah. Then A does not divide by B, or
Does
A
not
does not divide
divide
by,
into B.
oh, not divide into B or not divide into C. Thank you.
Great. And that is really critical. Shall we review the definition of divides? Let's
Yes.
let's review divides. We'll use an X and a Y. X divides Y if and only if Y, usually we say means, but that's okay, means Y equals X times K for some integer K.
Okay.
Shall we practice a few examples of divides and does not divide?
Okay. Yeah. Let's
Okay,
do that.
so some examples. Let's look at some examples where divides is true. Okay,
Hmm.
uh, 12 divides 36 because you help me. Because here's our definition. I'll put a box around it, and it's got two parts. Basically, it says X divides Y, or you can read it, X divides into Y means Y is a multiple of X. Some whole number of copies of X fit into Y. That's what we mean when we say Y equals XK for some integer K. It means X fits into Y a whole number of times. This K is our whole number. Does that make sense?
Yes.
And interestingly enough, X divides Y. X is going to be the smaller number. Y is the bigger number because X is dividing into Y. Does that make
Yes.
sense?
Yes.
They could, of course, be the same number. For example, 5 divides into 5. But Y cannot be smaller than X because if that was the case, no copies of X would fit into Y.
Hmm.
Does that make sense?
Yes.
So you help me. I claim 12 divides 36. So the X is 12, the Y is 36 because, and now you tell me what equation to write.
Because 36 equals 12 times 3.
Perfect. And do you see how 3 is playing the role of the K here?
Yes.
Great. Let's do another one. 3 divides 24 because, and you tell me why.
Because 24 equals 3 times 8.
Perfect. So the 8 is playing the role of the K.
Yes.
Now I want to do a fun one with you.
Okay.
3 divides 0, weirdly enough, because now
Because,
I said that this is the larger one, didn't I? But this is the
yeah.
one time that that's not quite right. There's an exception to every rule
Mm,
because 0 is equal to what?
equal to 0.
It
Oh,
is
0
equal to
is equal to,
0. Yeah, so 0 is our y.
uh,
This is the one time the y can be smaller than the divisor x.
mm,
What do we have to multiply this 3 by? In other words, what's our k that's going to make this a true equation?
and multiplied by 0.
Yep.
Okay.
So I say y is the bigger one. Well, they could be equal, and it is possible that y is 0. If you go back and look at the notes, in the notes, n divides 0 for any non-zero integer n. And you can go back and look at the notes and you can figure out why that's true, but it looks a lot like this.
Okay.
All right. Now let's look at does not divide. And let's write some true statements about does not divide.
Mhm.
3 does not divide 5. Let me show you why. Because 5 is not equal to 3 times k for any integer k. Do you agree there is no integer k that we could multiply times 3 to get a product of 5?
Yes.
Good. So this is one explanation. But there is another explanation that you could use if you like, and if you read the book, you'll see it. 3 does not divide 5 because when you take 5 and divide it by 3, that is not an integer. You see over here, when we take 36 and divide it by 12, we get the integer 3. Just
Yes.
divide both sides by 12. When we
Mhm.
take 24 and divide it by 3, then 24 over 3 is this integer 8. When
Mhm.
we take 0 and divide it by 3, we get the integer 0. So that's another way to think about divides. So, x divides y if and only if y over x is an integer. So if it's easier for you to think about it this way, that's fine. But this is most helpful for proofs. This definition up here is most helpful for
Okay.
proofs. Because once you use this, you have to name the integer, y over x is equal to k, and then usually you need to solve for y to do some kind of substitution. Huh. And it's easier just to use this equation where you already have an equation for y.
Okay.
All right, so that's a good refresher on divides. Now,
Yeah.
let's take a look at this. We'll leave our definition up and we'll leave the problem up
Mhm.
where we can see them. And now let's look at part A of the problem.
Mhm.
What does it ask us to do?
So part A asks us to write the hypothesis for a direct proof of the given statement.
All right, so we want to write a hypothesis. I think this was almost out of ink.
We got a lot of pens.
I do. I'm a pin freak.
Yeah,
Um,
fair.
it's so important for my work since I like to write everything for you. Hypothesis for a direct proof. And direct proof was the proof method that we've been using until we learned proof by contrapositive on Tuesday. So let's take a look. We've got the statement already written as an if then. Do you agree?
Yes.
So we could call this part our P, right? If P, then
Then Q.
Q. Great. We're on the same page, aren't we?
Yes.
All right. So we know what to assume. Tell me what we should assume for our
So,
hypothesis for a direct proof.
so we should assume if A does not divide 2B plus C, then A does not divide B, or A does not divide C.
So I'm very glad that you said that because that's a very common error. What you just told me to take for hypothesis was the entire statement that we wish to prove. Do you see what I
Mhm.
mean?
Yes.
We may not assume the entire statement that we wish to prove. We're trying to prove it. We cannot assume it.
Okay.
What we can assume is the hypothesis. And that's what we do when we're writing a direct proof. We assume the hypothesis.
Okay.
And there's no if in a hypothesis. We assume A does not divide 2B plus C. That's our hypothesis.
Okay. So that's it. All right.
See what I mean?
Yes.
Now, the next thing we want to do is part B. What does it ask us to write?
Asks us to write what we wish to show in a direct proof of the given statement.
Okay, so what we wish
Mhm.
for a direct proof. All right.
Mhm.
So we know about direct proof, right? We always assume the hypothesis. And what do we always wish to show?
We always wish to show the direct proof. Or,
We're going to use a direct proof to show the conclusion.
oh, okay. The
Okay.
conclusion.
So in fact, it might be helpful if I say, hey, P is our hypothesis.
Mhm.
Q is our conclusion for
Mhm.
direct proof, right?
Yes.
So we always assume the hypothesis when we're writing a direct proof of an if then, and we always wish to show the conclusion follows. So we wish to show this conclusion that A does not divide B or A does not divide C. Does that make sense?
Yes.
What's part C of problem 4?
Either write the contrapositive of the given statement.
Okay, let's do that.
Contrapositive. They need a refresh on the contrapositive.
Great. So let's just do a little refresher. Recall the contrapositive. So if the original looks like this for all x in D, P of x implies Q of x, that's when we just have an x for a variable,
Mm.
then the contrapositive is another if then, and it's the one that is logically equivalent to the original. It's an if-then, so it's a for all x in D. We don't change the domain. If not Q of x, then not P of x. Does
Oh,
that
okay.
look familiar?
Yes,
And what do
I
we
remember
know?
now.
Well, good. And what do we know about the relationship between the original and the contrapositive? Do you
Because they're
remember?
both logically equivalent.
They are logically equivalent to one another. For example, for all plants, X, if X is a rose, then X is a flower.
Mhm.
If X is a rose, then X is a flower. Well, that means the same thing as for all plants X, if X is not a flower, then X is not a rose. Because
Yes.
if X is a rose, it has to be a flower.
Mhm.
If it's not a flower, then it can't be a rose. Remember that
Yeah.
example that we looked at way back when?
Yeah.
Okay, good. So we're going to actually utilize this logical equivalence when we write proofs by contrapositive. All right, so let's write the contrapositive of this original statement. Now, this is actually a for all A, B, and C in D. Okay, D, the domain, is Z. But it doesn't matter. The form stays the same. P implies Q is logically equivalent to not Q implies not P, right?
Yeah.
So we always keep the universal quantifier and we keep the domain. We never change the domain. We don't even change the domain when we write the negation. So here's the contrapositive. Let's do it together. And it's going to be good review because we're going to have to remember De Morgan's laws. Here we go. The for all A, B, and C, and Z, we keep that. The for all is still a for all because we're still going to be writing an if-then. And every if-then statement is universally quantified. Do you remember that?
Yes.
All right. Now, here's our cue. It's an or statement. We call these disjunctions. But we want if not Q, right? So can you negate Q for me? What do you think the negation of A does not divide B is?
It would be A divides B.
Exactly. And when we use De Morgan's laws to negate Q, what happens to this or?
Becomes an and.
It does indeed. And then what happens to A does not divide C?
It becomes A divides C.
Very nice. So if A divides B and A divides C, then, and then we want to write our not P. What is not P going to be?
It would be A divides 2B plus C.
Exactly. Very good. What is part D?
D. We derive the hypothesis for a proof by contrapositive of the given statement.
Do you remember that proof by contrapositive is simply a direct proof of the contrapositive? See, this is our not Q. This is our not P. So we're really just going to be writing a direct proof of a different if-then. And that's the beauty of it, is it's not really a new proof method as much as the application of direct proof to the logically equivalent formulation of the statement which we call the contrapositive. So we want to write the hypothesis for proof by contrapositive. What should we assume?
So yeah, so we go with proof. So we should assume that uh, we should assume that A does not divide B. Oh wait, no. We should assume that A does not divide 2B plus C. Is that right? No, wait.
This
No.
is our okay. So
Yeah, I
so
was
I
focused on the wrong thing.
understand.
Sorry.
Right,
Sorry.
right, because you're looking at the original statement, right?
Yes, yes,
Okay. But now you see we're going to use the contrapositive statement and prove it directly.
yeah, okay.
So what should we assume?
Okay. So we should assume A divides B and A divides C.
Nice.
Yeah.
And you see the beauty of this hypothesis compared to the hypothesis for direct proof.
Mhm.
This hypothesis would not give us any equations to work with. It just tells us there are a whole slew of equations we don't get to use.
Yeah.
However, when we are looking at the hypothesis for proof by contrapositive, both of these are going to give us equations because we have divides now at our disposal. Does that make sense?
Yes.
Okay, what is part E?
Part E is write what we wish to show and improve by contrapositive of the given statements.
Okay, so what do we wish for proof by contrapositive?
So we wish to show that A divides 2B plus C.
Exactly. And this is a problem that is tractable. This is a problem you can do. Whereas if you tried to prove the original statement directly, you would have an assumption that gives you nothing to work with. And then how do you even prove does not divide or does not divide? Like, how would we even know how to get that done?
A good point.
And so that's your big clue that you might want to use proof by contrapositive is when a direct proof has a hypothesis that gives you nothing to work with, no proof money whatsoever.
Yeah.
So if you lean in on that idea that it's going to be a lot easier to prove the contrapositive. And once we've proven the contrapositive, we've proven the original because we know they always have the same truth value. So if the contrapositive is proven true, so is the original. They always have the same truth value because they are logically equivalent. And you can lean in on this definition. Just be careful when you're setting up your equations using the definition of divides. If you use K for your equation because A divides B, then you'll want to use a different letter when you write your equation representing that A divides C. Does that help?
Yeah, that helps a lot actually. Yeah. That
Great.
makes problem four like a lot more easier the more I look at it now.
Yeah, I was trying to walk you through the steps that would be necessary for you to come to this conclusion, but it helps to see the idea again.
Yeah.
The whole idea that some statements are just easier to work with in their contrapositive formulation. Is there anything else you want to look at?
Um, I think I want to look at problem number two.
All right. Do you want to read it to me?
Okay. It shows if all of x is an integer, no, for all x that are integers, uh, x times x plus 1 times x plus 2 plus 6 is divisible by 3. So we have to prove the statement. I was had a slip up there at first.
So we want to prove this.
Mhm,
You were in class on Thursday.
mhm.
I want to show you the class notes. Is that okay?
Yes.
I'm going to share my screen. Move this stuff out of the way. So we talked about proof by cases and how it's a valid argument form. And we looked at the steps for writing a proof by cases. We identify the divisor D, and to find that, we look at the conclusion. Then we assume the hypothesis and use the QR theorem to set up D cases, where each case corresponds to a possible remainder when the variable in the hypothesis is divided by D, and that variable will always represent an integer. And in each case, we prove the desired conclusion. So even though we didn't have time to thoroughly go through example 3, I at least showed you some of the algebra involved in that problem. And we talked about how this expression, x times x plus 1 times x plus 2, is the product of 3 consecutive integers. Do you remember that?
Yeah.
So if we scroll to example 3, ah, I hate when it does that. We proved that just this product, x times x plus 1 times x plus 2, is divisible by 3. And it's already written in if-then form. Just like we wrote it in if-then form. We're going to write this in if-then form too, okay?
Okay.
When we write this in if-then form, it's going to be if x is in z, then this expression is divisible by 3. That's all that's going to be different, okay?
Okay.
So how do we start? We assume the hypothesis because we use direct proof for proof by cases. Do you always have to? Of course not. But for us at our level, you can trust me when I say all our proofs by cases will be direct.
Okay.
So we let x be an element of z. What do we wish? We wish to show that this expression, this product, x times x plus 1 times x plus 2, is equal to 3 times k for some k in z. Do you know why I'm saying that that is our wish?
That's our conclusion.
That's right. And why am I writing this equation when I'm talking about x times x plus 1 times x plus 2 is divisible by 3? Do you understand the translation from that conclusion statement to this equation?
Yeah, a little bit. Is it because like we wish to prove it? We want to show it?
Yeah, and I just want to double check that you're comfortable with the idea of something being divisible by 3.
Yeah.
that if an expression, whether it's this expression or any expression, is is divisible by 3, that means it equals 3 times some integer. Here I'm calling it k.
Yes.
Are you comfortable with that translation?
Yeah. A lot more
Yeah.
now. Yeah.
hmm So step one is to figure, of course, after it's written as an if then, is to figure out what D is. What are we dividing by in this problem?
B
Well,
is 3.
it's 3, right? Good. Once we've discovered our divisor, then we set up our cases using the QR theorem. And this is the new thing that we've never done before Tuesday. We simply write, and you can look at all the examples, and you can look in the book, all the examples in class notes. By the QR theorem with D equals 3, you're just talking to the reader and telling them, hey, we're getting ready to use the quotient remainder theorem, and our divisor is 3. It's polite to let them know what we're getting ready to do. We know, well, x, you take the integer in your hypothesis right here, our x. X could equal 3q, or x could equal 3q plus 1, or x could equal 3q plus 2, where q is in z. Now, let me ask you a question. Do you understand why we can say that there are these 3 cases?
Mm, Not really, no.
Good.
Yeah.
It's good for us to understand this.
Okay.
Do you believe x is an integer?
Yes, because it says let x be an integer.
Great. Do you believe that we can always divide an integer by 3 and get
Yes, because
one
3
of,
is also, oh, sorry.
go ahead.
I was just going to say yes, because 3 is also an integer.
What are the possible remainders? What are the legal remainders when we're dividing by 3?
0, 1, and 2.
Correct. So the point is, we do not, excuse me, I'm just closing my blinds here. We
Okay.
do not know which integer x is. All we know is that it is some integer. Do you agree?
Yes.
We know we can divide it by 3, but we don't know which remainder we would get because we don't know what x is. For example, x could be 6. If we divide 6 by 3, what is the remainder that we would get?
0,
Good. But maybe x is 7. If we divided 7 by 3, what would be the remainder?
1,
Exactly. But x could be 8. What's the remainder we get when we divide 8 by 3?
2.
You see, the point is, we don't know what kind of integer x is. We don't know if it's a multiple of 3, or if it leaves a remainder of 1 when it's divided by 3, or if it leaves a remainder of 2 when it's divided by 3. What we do know is one of these 3 things is guaranteed to happen. Does that make sense? The quotient
Yeah, it makes a
remainder,
lot more sense.
yeah, the
Oh,
quotient remainder theorem says you can divide x by 3, and you're guaranteed you're either going to get a remainder of 0 or 1 or 2. So if we want to prove this statement about all integers, and this statement is about divisibility by 3, we need to introduce some 3's into our work, and applying the QR theorem with D equals 3 is the perfect way to rewrite x so that we can see a 3 in it.
yeah, it makes a lot of sense. Yeah.
So now, in each of these 3 cases, we're going to do the work to show that when we look at x times x plus 1 times x plus 2, it will equal 3 times some integer k. In each case, we have to show that. But you see, it's like this. When we are proving what we wish, which is that 3 divides x times x plus 1 times x plus 2 in case 1, we're proving that this conclusion holds for 1/3 of the integers. Which third? The third of the integers that are multiples of 3 and have a remainder of 0 when they're divided by 3. And then when we move to case 2 and prove this wish, this conclusion in case 2, then we've proven the conclusion for another third of the integers, the ones that look like 3q plus 1. And then when we work case 3, we kill it for the last third of the integers when we prove that 3 will divide that product of 3 consecutive integers. Do you see what I mean? So we're kind of killing the proof in thirds because each of these cases represents a whole group of integers, 1/3 of the integers to be exact. And these are glued together, and we're just treating them kind of like one big kind of block number where this is our 0, this is our 1, and this is our 2. Does that make sense?
Yeah.
So here's the algebra. For case 1, we take our supposition that x looks like 3q. That's one of the three things that could happen where q is in z.
Yeah.
So remember, our wish is to look at x times x plus 1 times x plus 2 and show that that is going to be a multiple of 3. In other words, we need to be able to factor a 3 out of x times x plus 1 times x plus 2. So we just use substitution, and it falls right out. X times x plus 1 times x plus 2. Well, we're putting in the 3q for this x, right? And then we put in a 3q for the next x. Then we put in the same 3q for this x, and we get this expression. Don't multiply it all out. That's too much work, and it doesn't help. Just pull out the 3 out front. That's our 3 to show 3 divides. And this big thing is our k. And it's an integer because sums and products of integers are integers. See what I mean?
Yeah.
Then we move to case 2. This is when x looks like 3q plus 1. So now we plug in 3q plus 1 for x. And since 3q plus 1 is a binomial, we have to use parentheses here. And then when we put 3q plus 1 in this middle factor, it becomes 3q plus 1 plus 1 more, which of course is a grand total of 3q plus 2 for the middle factor. And do you see why x plus 2 becomes 3q plus 3 for the last factor?
Yeah, because it's 3q plus 1 more and 1 more. Yeah.
Exactly. Again, don't multiply it all out. Try to figure out where you can factor a 3 out. Well, we can't factor a 3 out of the first factor because there isn't a 3 in the 1. We cannot
Mhm.
factor a 3 out of the second factor because there's no 3 in the 2.
Yeah.
But see how we can pull a 3 out of the 3q plus 3,
Yes.
leaving behind q plus 1. So now we have our 3 out front, and this long expression, these 3 binomials multiplied together, those are the factors that build our q that's an integer. Does that make sense?
Yeah.
So we showed that x times x plus 1 times x plus 2 looks like 3 times an integer, where that integer is this big old thing.
Mhm.
Well, we're 2/3 of the way home. We only have 1/3 of the integers left to deal with, and that's the integers that look like x equals 3q plus 2, where q is in z, of course. And it's the same game. Do you see why x has become 3q plus 2 here, the first factor x?
Mm. Yeah, I think it because we already have x equals 3q plus 2. So yeah.
Exactly. And do you see why the x plus 1 becomes 3q plus 3?
Yeah, because 3q plus 2 plus 1 more.
Exactly. And then, of course, you understand why x plus 2 becomes 3q plus 4.
Yep. 3q plus 2 plus 2.
Perfect. And now we're on the hunt. We're on the hunt for a three. And it's not in the first factor because of the daggum two. It's not in the last factor because that four messes it up. But looky here in the middle, we
Yep.
can pull a three out of this binomial factor, again, leaving behind this pleasant little monomial q plus one. And what's underlined here becomes our great big K that is an integer. So in each case, we showed 3 divides x times x plus 1 times x plus 2. All right. Do you have any questions on that?
Mhm. Only question is like what changes if we get like some different like number one where we get n squared minus 3n plus 7, which is always odd. So I guess my
What?
question is like, can we do number one?
Yeah, because there's a different D. It is
Uh,
critical that you pick the correct divisor D.
Okay.
Here was our first proof by cases.
Oh, okay. I see a similarity. N squared plus 3n plus 5 is odd.
And when we're talking about an expression being odd, we're talking about what it looks like after we have divided it by 2.
Mhm.
What do numbers that are odd look like?
Usually it's 2k plus 1, right?
That's right. Or you could call it 2q plus 1 because it's 2 times an integer plus 1. The
Yeah.
divisor is 2. So instead of saying that this is even, which means 2 would divide n squared plus 3 and plus 5, kind of the way 3 divided that product of 3 consecutive integers, we're saying, nope, we get a different remainder. We don't get the remainder 0 when we divide n squared plus 3 and plus 5 by 2. We get a remainder of 1. That's what it means to say this expression is odd.
Okay.
So if the conclusion is about something being even or odd, your divisor is 2. If the result is something like the second example, where we said, hey, x squared looks like 3k, or x squared looks like 3k plus 1, you need to realize, oh, we're talking about dividing by 3 and saying the remainder is either 0 or 1 when we divide x squared by 3.
Mhm.
So you look to the conclusion to figure out D. Once you know
Okay.
D, then you know how many cases you're going to have. You always have D cases because there are D remainders. What are the remainders when we divide by D equals 2?
The remainders are 0 and 1.
Exactly. So we assume N is in Z. You always assume your hypothesis. We have this wish that n squared plus 3n plus 5 is equal to 2k plus 1. See, we're saying, oh, when we divide n squared plus 3n plus 5 by 2, we get a remainder of 1 every time, no matter what n is. But there are no 2's in n squared plus 3n plus 5 that will be helpful. This exponent of 2 doesn't help much. So we introduce the 2 by using the QR theorem with d equals 2. N is an integer. We're guaranteed by the QR theorem we can divide it by 2 and we'll either get case 1 where n looks like 2q, or when we divide n by 2 it looks like 2q plus 1.
Yeah.
And then in each case we look at n squared plus 3 and plus 5 and we use substitution and we get it looking like 2 times an integer, something, some big expression that'll be a k plus 1 left over. It works in both cases. See that?
Yep.
Do you have any questions?
Mhm. I think I'm good for now. Yeah.
I just want to go back to this number 2 with you and let's first write as an if then, shall we?
Sure thing.
Because it is universal. And we did learn some basic things about proving universal statements. And one of the things we learned was do this good step one, write it as an if then. So, do you know how to write this as an if then?
So the first part is, I guess, say if all integers of x, no, if there is some integer of x,
Yeah, if x is in z, so you could write
yeah,
if x is an integer.
if x is an integer, then x times x plus 1 times x plus 2 plus 6 is divisible by 3.
Good. And another way to think about it is if x is in z, then 3 divides x times x plus 1 times x plus 2 plus 6. Either way. But now we've got our hypothesis that x is just an integer, and this is our conclusion, which is our wish. And what's our divisor?
Our divisor is 3.
So how many cases will we have?
3 cases.
Do you know how to set the cases up?
So yeah,
By the QR theorem with D equals 3. Let's give ourselves our hypothesis. Let x be an element of z. By the QR theorem with D equals 3, we know. Can you tell me the three things that are the possibilities?
3q plus 1,
Well, that's one of
or
them. I'm
yeah,
going to say 3q first. X equals 3q. We're applying the divisor 3 to
mhm,
the x. When we play divisor games, you have to have something that's getting divided, okay? We need an
okay,
equation.
okay.
Or, what's the next one?
X equals 3q plus 1, yeah,
Good. Or, what else could happen?
or x equals 3q plus 2.
Great. And for all these Q, oops. Oh, okay. Q is in Z, right?
Yeah, k is in z, yes.
Yeah,
I
but
mean, q is in
Q
z.
is in Z, right?
Yeah,
So we actually now have our three cases all set up. Case one, case two. So we'll suppose this in case one, that x is equal to 3q. We'll suppose x equals 3q plus 1 in case two. And what will we suppose in case three?
x equals 3q plus 2.
And what do we wish to show in each case?
It was to show that 3 divides x plus 1 times x plus 2. I mean, x times x plus 1 times x plus 2 plus 6. Yeah.
That's right. We wish to show 3 divides x times x plus 1, good, times x plus 2 plus 6. And I'll just say, let's just dig into that and then we'll be done. That means x times x plus 1 times x plus 2 plus 6 looks like what? What does it mean to say 3 divides that?
It means to say,
That this big thing looks like, do you want the definition of divides again in front of you? Let's get the definition of
yeah,
divides.
yeah,
Oh, no, it's great. It's handy to have the definition of divides.
yeah.
All right, there's the definition of divides.
Okay. It means y equals x times k, where k is in z.
Okay,
So,
so what's our x and what's our y? Let me put these a little closer to each other so that it looks right.
so our x is 3 and our y is x
This,
times, yeah,
X plus 1 times x plus
times x
2.
plus 2 plus 6.
So what is it supposed to equal then?
It should equal x times x plus 1 times x plus 2 plus 6 equals 3 times k,
Great.
where k is in C.
Perfect. See, you did
Uh,
it. And that's awesome. See, now you're getting it. Just one step at a time, right? So
yeah,
you're shooting for that. You've got three cases. It's going to be a bear of an algebra problem, but I showed you the hard part of the algebra by making it easy in the class notes example 3. The only difference between this expression and the one in example 3 is I added a plus 6 just so it would be a little different. You'll still be able to factor a 3 out of everything
yeah.
in every case.
Hmm.
Okay. Well, that was a workout.
Yeah, yeah,
Thank you so much for
yeah.
coming.
Yeah, yeah, this really helped me out, like, because I didn't go to the office hours the first time and I was on the exam. I really did not know what I was doing.
I really wish people would come to office hours or ask for different office hours. Actually, somebody did ask for office hours tomorrow night, and we're having office hours tomorrow night. I'll announce the time when I confirm with the student that the time I suggested is going to work for her.
Okay. What time is that going to be? Because is that going to cover that could be the exam review?
Yeah,
Okay, perfect.
we'll start reviewing for the exam. It's going to
Yeah,
take several office hours to really get through everything.
yeah, fair.
All right.
Yeah, so I'm gonna probably wake up early tomorrow, do my special homework, and then I'll meet you guys at the office hours.
Okay, and I'm going to put up the web assign for Contrapositive in the morning, but you'll
All
have
right,
until Thursday to work on it.
cool.
All right.
All right,
Thanks for,
it's nice seeing you, Professor.
it's nice to be in the room with you. Thank you so much.
Mhm.
Good
Have a good
night.
night. Mhm.